Hi, I'm Tim Tyler and this is a video about sensors, processing and actuators. I'm going to be illustrating what I mean using this device, which is a small Nokia portable computer. So to start with, the sensors here, we've got a keyboard here where you can input textual information. There's a touchscreen area up here where information can be put in by pointing at things, and then there's a camera here which can supply more information. That's how information gets into the device. Then it's processed in the device's central processing unit, which is also attached to some memory, and then information comes out of the device here on the screen, which is its main actuator, and also on the sides where there's two loudspeakers. If you look at the cybernetic diagram corresponding to the device, you'll find that it has sensory inputs, a central processing area, and then a range of motor outputs. This is similar in many respects to the way in which biological organisms operate. Organisms take in information from their environment using their organs of perception, process it in various ways, and decide on what they're going to do, and then use their organs of action in order to execute their plans. In many respects, animal nervous systems represent this kind of diagram in its purest form. Animals have dedicated sensory organs such as eyes and ears, and then they process information in another dedicated organ, the brain, and then have more dedicated output organs such as hands and mouths with which to effect changes in the world. If we return for a moment to our device, we'll see that there's some complications to the model. In addition to having an input device and an output device and a processor, there's various other properties that the device has. It eats batteries and spits out heat, and has a variety of structural properties. One limitation of this type of cybernetic diagram is that it doesn't include reflexes. So to illustrate, if I press a button on the keyboard, then information goes into the device from my finger, and then it doesn't go via the CPU. Information comes straight out again into my finger to provide me with some feedback. And I consider that to be a situation analogous to spinal reflexes within mammals, where the information doesn't get as far as the brain, but for performance reasons just comes straight out of the organism again locally. So, having said what I mean by senses, processing and actuators, let's consider some of their properties. A human has a relatively limited number of different types of actuator. So almost everything is done with contractile muscle fibres in a human. There's fast twitch fibres and slow twitch fibres, but almost everything is done with muscles. There's also kind of pheromone outputs and glands within the body that are operated by non-muscular means, but almost all the outputs are muscular. There's a bit more diversity in the sensory system, so we've got eyes and ears and nose and mouth, each of which have their own dedicated set of cell types for sensing the outside world, so there's a bit more diversity there. And if you look inside the brain, then although superficially there's glial cells and neurons, the neurons actually come in quite a wide variety of different types, so there's quite a lot of complexity inside the brain as well. If we consider what happens inside modern computer systems, then there are some differences. There's still a range of different types of sensory input. However, this time there's a broader range of motor outputs. So if we consider the technology required to make a dot on a computer screen, it's quite different from that required to make a dot on a piece of paper, which in turn is quite different from that required to make a noise come out of a loudspeaker. And if you look at the world of computer muscles, then there's servos that go back and forth, and then there's motors that go round and round, and hydraulic systems and pumps, and there's quite a range of different output devices, even if we consider things that are analogous to muscles as well. The situation regarding processing inside computers is even more different. At least in theory, you can construct a whole processor inside a computer using nothing but wires and NAND gates, leading to extremely low component diversity. If you're actually building a real computer, you probably want more diversity of components than that. So there's several spectrums by which processing units inside computers can differ. First one is memory density. On one hand, you've got random access memory, which stores lots of information quite densely but can't process it at all, and on the other end of the spectrum you've got microprocessing units, which aren't so good at storing information but are much better at processing it. Then there's the reprogrammability spectrum. So on one end of that you've got field programmable gate arrays, which are highly reprogrammable, and on the other hand you've got specialized microprocessors, which typically simulate a serial machine of some kind or another and aren't very flexible at all. Then there's the issue of how much money you've spent on miniaturizing the components. If you're simulating a serial computer, then what you want is high performance units, and you don't need all that many of them, so you're prepared to spend a fair amount of money on the units that you do have. Whereas if you're building a parallel computer, you're often prepared to trade component quality for component quantity. So instead of buying a small number of high performance components, you buy a large number of low performance components and use them in parallel with one another. And then lastly is the issue of reversibility. If you're doing reversible calculations, then you don't need to spend kind of space within your processor building channels for heat to be dissipated and other channels for power to come into the system in the first place. Instead, you can have your processing units close together, whereas if you're doing the types of calculation where information needs to be lost, often you do need to have those channels present in order to give power to the system and to allow it to dissipate heat. So components vary, at least ideally, in a number of ways, but there's still only a relatively small number of different components inside a central processing unit of a computer. A low diversity of components has some benefits. In particular, it allows you to concentrate your research and development budget into a small number of areas, and so in those areas you can make more progress because you're concentrating your energies on them. Areas where that's happened in the computer science field, the processing units within computers, transistors, they have been made high performance in a relatively short space of time as a result of concentrating energy on the problem. Similarly, pixels in LCD monitors, also high performance units. Vision is an important area for both input and output for computers, so the sensors inside digital cameras and the screens computers use to communicate with humans, both of them contain thousands of individual sensors, and they're all identical to each other basically, so massive parallelism, and research can concentrate on just solving one problem really. So that has big payoffs in terms of the rate of development if you can concentrate your research and development budget onto just one problem. The next issue regarding sensors, processing and actuators that I'd like to draw your attention to involves the issue of moving parts. At a low level, the universe consists of elementary particles, and unless they move around, nothing happens. So, in a fundamental way, all computer components have moving parts. However, there's a difference in the utilization of them within the different categories of computer component, and actuators have more moving parts than processors or sensors do. The reason being that actuators have to actually engage with the world and make some changes to it. So, in order to do that, they have to have moving parts, really. The robot equivalent of muscles have the most moving parts of all, so servos and motors and that kind of thing. The problem with moving parts is that they go wrong and wear out. If you've ever repaired a vacuum cleaner or a bicycle or a tape recorder or something like that, you'll be familiar with the principle that the moving parts are the parts that go wrong most frequently. And the reason is that they suffer from wear and tear due to friction. They lose their lubricants, they get worn, and basically they just wear out more rapidly than the other parts of the machine. The situation regarding machine actuators wearing out more rapidly than other components is exacerbated by their poor self-repair capabilities. If you consider biological organisms, by contrast, these can repair moving parts once they've worn out by using cellular self-replication mechanisms. However, machines can't take advantage of self-replicating mechanisms currently, partly because the technology is not available, and even once it becomes available, it will probably be hard to get FDA approval for deploying self-replication in the field. So this makes machines fundamentally more brittle and harder for them to self-repair themselves. The problem with moving parts results in a delay in actuator development, especially actuators such as servos or motors, where there are moving parts that move things around in the external world. The effect of this is that robots, although their sensory systems are kind of up to a reasonable level, digital camera eyes are kind of have similar capabilities to human eyes in many respects, but their motor units, their actuators, are of much poorer quality, so their movements appear uncoordinated and lacking in precision, and lacking in strength and stamina, and just generally of a poorer level, and they don't seem to be able to move properly in many respects. And this is a problem that seems like to persist into the future as well. Actuators will lag behind sensors in terms of the rate of their development, because of the problems associated with moving parts, basically. That's the conclusion of my video about sensors, processing and actuators. Enjoy.